Lesson 1-13. Today, we're going to take a look at what we call regressions. If you look at your learning objective, what we're focusing on today is we're going to look at data and come up with what we call an appropriate function type. Not only that, we'll construct a model. Model being a key word that the calculator is going to call a regression. I'd encourage you to write that down because that's the button we're going to be clicking here in a moment with technology. I have my Desmos already open. I would encourage you to open yours up because we're going to be using it all class. So go to your Google Classroom and open up Desmos because we will be using this all class, like I said. Okay, with that, I'm going to get started. By the way, the second learning objective is basically the same as the first. We're using technology to model a function for a situation. Okay, so today, we're dealing with, like I told you, regressions. It's a major component of AP Pre-Calc curriculum. You can read this on your own. I'm not going to waste my time here reading this, something you can do on your own, but I'm going to use Desmos. You can also do this with Inspire. You can check other videos online for that, but I'm going to use Desmos today. So first, let's look at example 1 here. It says the age in weeks and the weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table below. There's the data. Secondly, or part A here, says the weight of the baby 2 weeks after birth can be modeled by this function W given by all of this. My first question for you, what is in the place of X? Because I don't have an X in this problem. T. Okay, very important for you that once you notice that, I would go to your table and put an X because it's going to matter for Desmos in a moment. Just put, that's X. I'll just do an arrow, which means that this is X. What is W O T? Y. Okay. And yes, if you're going to ask, by rule, X data comes first, Y goes second. So go over to your Desmos. Mine, I know, looks different than yours. If you're at full screen, I know it's going to look slightly different, but it's the only way I can fit everything on. Hit the plus and choose table, or you can just type in table if you prefer. Type in table and get yourself a table up. Let's type in our values. So my X values, or T values, you could say, are 4, 5, 6, 8, and 12. Type those in, and then type in your Y data. If you're watching at home, just pause the video until you get those typed in. Okay, one of the things that's not required to do, but I'm going to do all day because it is helpful for us long term, is to see this as a correct scatter plot. Hit the zoom fit button. It looks like a magnifying glass, the plus. This problem tells us it's a linear equation. It actually doesn't use the word linear, so I should just ask you, that does show us a linear, but it doesn't say it's linear. When you look at this, what shape does it appear closest to resemble? A line. So what I want you to do now is up by where your variables are, you'll see these dots with the line through them. What this is going to do is it's going to generate an equation to go through the dots. Go ahead and click that button there. Now when you do that on Desmos, the automatic regression is linear. That's the automatic. If you had a different type, you would choose something different there, but we're saying it's linear. This right here is going to be our equation. Let's go ahead and copy that over. I'm just going to copy and paste it. You go ahead and write your equation down in your packet. That is the equation that we're going to be using in a second. Oh, I'm not even following my instructions. Sorry. Let me follow my instructions. Part AI says write 2 equations that could be used to find the values for constants m and b and the expression for w of t. Okay, so here's what this means. We want to make sure that without a calculator, you know what the process would be. Now, this type of question, you're always allowed a calculator. So here's what the process would be. If you were writing, you would take this equation right there, and you would plug in 2 data points. Now, why it says 2 is because right there it says 2. 2 equations. We would choose 2 data points, and we could choose any 2 we prefer to solve for m and b. So looking up here, you could choose any 2 equations you want, or any 2 data points. So you could choose like this data point. I'll call this data point 1. How about just P1 for point 1? If I plug this in, 5 would go in for what value? Look over here. What's 5? T. And what's 4.4? WT. So WT comes out. WT is 4.4. We don't know what M is, but we know T is 5. Now, on the t part, you put that in parentheses, plus b. That's one equation right there. That's 1. Now, my second point, again, you can pick any point up there. Y'all just call out which one you want me to use. One that starts with an 8, how about that? We'll use this as data point 2. This will be my second equation. You would plug in those points. Again, 5.1 is the WT. We don't know M, but we know T is 8 plus B. Now, if you wanted to use algebra, you could go through this process to solve. But those would be my two equations. That's AI. That would get you a point right there. That's how you would get that point. Now, secondly, it says find the values for M and B. This is, I do not ever use algebra myself. I use the calculator. It's too easy, and it doesn't make mistakes. This is our equation here. What value represents M? I hear 0.185. And remember, you have to have 3 decimals. And what value represents B? 545. I cannot round this one because you need 3 decimals for my class. So this one, the values as given, that would be it. So that's how you would get your points for both AI and this is AI right there. And this would be AII. I know that sounds weird, but that's how you would keep track of what everything is. Okay, does that make sense on how I did that?
Yes.
Pretty simple, right? You just plugged in first time, but I used the calculator to solve. Okay, go to your next slide. You have part B. On part B, it says using this model from part A, BI, what is the predicted weight of a baby that is 10 weeks old? Now, here's the key. Whenever you get the number, circle the number with whatever you want to call it, the units or whatever type it is. This says 10 weeks old. Go back over, 10 weeks old. Is that a T value or a WT value? What is, if it's weeks? And yeah, you can look over here and it tells you as well. T is weeks. Okay, so T represents what in this problem? Sorry, what variable? X. Okay, so what we're going to do in our calculator is we're going to say X equals 10. So now come to your equation. Do not delete anything. Go to a new line and type in X equals 10. Don't type in T equals, type in X equals. Everybody cool with that? All right, you'll notice that it intersects your graph. Go ahead and click where the graph and that new line intersect one another. So it says, what is the predicted weight of a baby that is 10 weeks old? Well, what do y'all think the predicted weight would be? Y'all catching on quick. It's going to be 5.395. The weight, which is a W value, I'm going to write it this way. W of 10, we would guess, is going to equal 5.395. And this is in, what units is this? Kilograms. Kilograms. That would be my weight right there. Questions over that? Okay, I'm going to keep continuing on. In this same line of thinking, part BII says the weight of a 6 baby is 5.3 kilograms. What is the predicted age of this baby? Okay, something has changed. This time, on AII, it says the weight is 5.3. What is weight? Go back over here. Weight is our Y. So this time, they're telling us the Y is 5.3. Any ideas on how you think you would solve this one? Very good. I'm just going to change this equation here. Y equals 5.3. Again, click on the intersection. Now, in my class, you need how many decimals? 3. You have to have 3 decimals. So we have to have 3 decimals. So the answer would be here. This is in weeks. So you could say T equals if you want, but as long as you say weeks, the weeks would be 9.48. Technically, you can round or truncate. I'm going to be exact on this video here. Would this be a 6 or should it round to a 7? 6. 9.486 weeks. All right. Now, as the slide says at the bottom, don't delete this. We're going to return to it in just a second. Okay. Am I ready? Are y'all good? Move on. All right, good. Now, next thing we're going to look at, it's called residuals. The next thing we're looking at now is residuals. So what a residual is it's basically a measurement of error. Error. I know that sounds weird coming out of my Texas. What do you call it when you accent? Yeah, I'm not talking about air you breathe here. I'm talking about how much something is correct versus incorrect. It makes sense what I'm talking about here. Error, ERROR. Okay, a residual measures the error. So what is a residual exactly? It's the actual value minus the predicted value. The predicted value here, check this out. The predicted value is like the W value itself, like when you use the calculator. The actual is from the table. Let me do it this way. It's like what you get in the table minus what the calculator thinks it's supposed to be. That's what the residual is. You'll see it labeled this way, where the y is the true table value, and the y with what they call a hat, y hat, is the calculator. So when I look at this here, I have just an example to show you. This over here is what we call a typical scatter plot. Next to it is a residual. A residual, no matter what equation you're looking at, a residual will have a center line like this. This is the prediction. Go ahead on this red line right here, put that this is the predicted amount. This is the prediction. So on a residual, you'll always have a flat line. Always, always, always. It'll be flat like that. That's the prediction. What these dots are is how much the prediction is away from the actual value. So let me be clear. Do you see these purple dots right here? If you counted up how many purple dots there are here, there's always the exact same amount here. What this does is it measures off how much each one is. So this one, at the coordinate 70, 21, here's my line for the prediction here. I'm going to go ahead and put this prediction. Here's my prediction. Now, is 21, or at this point here, 70, 21, is it above or below the prediction? It's below. Now come over here. You see how it's also below? The residual value would be called -5. That's the residual. That right there is your residual. What that means is it's 5 different. It's 5 different than the prediction. So if the real value was 21 and it's 5 underneath, what was the predicted amount right here? What would the predicted amount be if I added a predicted amount right here? Let me do it in blue. What would the predicted amount be? Okay. What would the predicted amount be right here on the line? What would be the coordinates of that predicted amount? Does anybody know? 70, 26. How'd you get 70, 26? Well, using the residual, how much was it off? 5, and it was 5 underneath, which means this point's got to be 5 above. What's 5 above 21? 26. Does that make sense? That's how a residual works. Okay, so let me see if I answered that. 2 coordinates are shown in the scatter plot and residual point where the units are in thousands. What is the predicted price of a vehicle with 70,000 miles? So the predicted price would not be $21,000. So these prices are in thousands. That's what the actual value was. The actual value was 21,000. What's the predicted cost or price of a vehicle with 70,000 miles driven? $26,000. That would be your predicted price. That's the predicted price. Let me put that in there. Predicted price. What was the actual price? 21,000, but our predicted is 26,000. So that's how a residual works. Now with that, let me talk about why we use them. When you use residuals, you can tell, number one, if the plot is good or bad, like a regression. You can tell if your regression is good or bad using the residuals. If there's no distinct pattern, it is a good residual. I'll say that again. This seems backwards. If the residual has no distinct pattern, it's a good table. Now look at this one. Do you think this one's good? Do you think this line is good or bad when you look at it? Don't ignore the slide on the left. Just looking at the line. Does the line go through most of the points decently, you think? Yeah. So what we're going to see is we'll see a residual that has no pattern. If your residual has a pattern, what that means is your original was not a very good equation. So what am I trying to say? Let me choose quadratic. That looks decent. Let me choose a different one. Let me get one that doesn't work. Okay, this one's kind of bad. But the worst, no. Got excited. Let's just leave it as it is. I'll show you as we go. Okay, so in example 1, we're coming back to it. Remember how I said don't delete this data? Now we're going to do a residual. We want to know what's the residual of a baby that's 5 weeks old. So here's what we do now. Come over to your calculator, and on the side, right under linear regression, you see where it says residuals plot? Go ahead and click that button now. Plot your residuals. Now really concentrate here because you need to catch this. After you hit plot, you'll then need to hit zoom fit on this residuals part because it's going to change the zoom away from this. So residuals, plot. To help us out here, it says, what's the residual of a baby that's 5 weeks old? Now, remember, weeks old was which variable? X. This is when X is 5. So if you need help again, you can type in X equals 5. So I'll change this from Y to X equals 5. It's this residual right there. That's the residual we're looking at. If you need help finding it, that's it. It's not letting me click it. There it is. Now it's clicking it. Are y'all getting the same point as me? Okay, that's going to be our residual. So I'm going to copy this over. Okay, so the residual that's 5 weeks old. Here's what that means. This means the actual data point. That right there is the actual. The x-axis represents the prediction. This x-axis, this is the prediction. Is the actual data greater than or less than the prediction? Less than. Yeah, what this is meaning is that the actual weight, let me write it, let me just type it in. What this means, here's the interpretation. The actual weight of a 5-week-old baby is 0.07 kilograms less than the predicted weight. Now I'm going to go get the actual values in a second. Weight of a 5-week-old baby. Okay, just to be clear, look on the original table. What was our actual data for a baby that was 5 weeks old? What was our actual data? 4.4. So the actual weight of a 5-week-old baby, I'm going to put this in parentheses, is 4.4 kilograms. Is 0.07 kilograms less than the predicted weight of a 5-week-old baby. So what would be the predicted weight of a 5-week-old baby? If you're not sure, zoom back out on the real line. I'm going to go back to zoom fit. I'm going to zoom fit this one. And what was the... Sorry, I can't tell which one I'm hitting here. There it is. You see how it's predicting at 4.47? Why am I getting 4.47? What's off here? Am I just doing bad math? 4.47 kilograms. Oh, 0.07. There we go. I didn't realize it was 0.07. I was adding 0.7. Okay. So notice, you see how they're 0.07 apart? This is 4.4. This is 4.47. Y'all realize that? Yeah. So that's what the residual is telling you. So finally, if a baby that is 7.5 weeks old has a residual of negative 0.7 kilograms, what was the actual weight of the baby that was 7.5 weeks old? So to help you out on this, I'm going to give you the formula again. The residual, I'll do capital R for residual, is equal to the actual minus the predicted. Y'all remember that? That was the formula from the previous slide. On this problem, what does it say the residual is? Negative 0.7. If that's the residual, and they don't tell us the actual, that says... Okay, thank you. I'll give it to him. All right. We don't even know any of that. Let's go find out. Let's go find 7.5 weeks. Is that a T? Is that an X or a Y? Okay, this is an X. So I'm going to type X equals 7.5. And what we're going to do here is we'll type in X equals 7.5. We hit residual. I'm going to zoom fit on the residuals here. No, I won't. It's not on there. I'm going to zoom fit on the line. The actual weight. No, this is not actual. This is the predicted. I'm sorry. I keep saying the wrong thing. The predicted weight. Are y'all getting the predicted at the same values as me? Yeah. Okay. That's the predicted weight. So we're going to plug in our numbers and we're going to come up with what the actual weight would be for a 7.5-week-old baby because we don't have that in our table. If the predicted weight, we don't know the actual, that's regular Y, minus the predicted weight of 4.9325. Now we could round that, but I'm just going to leave it like that. How would you solve for Y here? That's right. All you have to do is add 4.9325, and you would have the actual weight of the baby, 4.9325. If you add that like that, now we know what the actual weight is. I'm just going to go type this in right here to make sure I don't make a mistake. Negative 0.7 plus 4.9325. That's going to be our weight right there. The actual weight, and this you could round if you wanted to. The actual weight, which you could write Y if you wanted to. The actual weight would equal 4.2. I'm just going to write all four decimals. 2325 kilograms. So that is using regressions. All right, example 2. I'm going to refresh my data here. You can go ahead and make that disappear. We have a table of ordered pairs here. This time, we're going to graph it and use a logarithmic regression. I'm going to go ahead and box that up. This is a new word, logarithmic regression. I'm just doing that for today, so we see something other than a line. So let's type this in. Again, how do you get that table up to begin? You can hit the plus, or you can type in table. Type your values in. All right, I think I have mine in. I'm going to hit 2 buttons. I'm going to hit the zoom fit first to make sure I can see the whole. This is called a scatter plot right there. The table itself is called a scatter plot. That's what they call that. So I hit the zoom fit so I can see my scatter plot, and now I'm going to choose logarithmic regression. How do I get to regression again? The line with the dots. That's where you get regression. We're going to choose logarithmic, not linear. Make sure you choose logarithmic. They both start with the L, but these are totally different. Choose logarithmic, and don't choose logistic either. Logarithmic is the one you want. All right, finally. Look at that. All right, here we go. Finally, we're up and rolling. That was the longest delay ever. Okay, so we have to first, on AI, it says write 2 equations that could be used to find the values. Now, this is if you're going to not use a calculator. How would you do it if you were not going to use a calculator? Well, you would take these equations they gave you, and you would plug in values. This says x and y. This is not very good considering this said, where y equals f of x. So y is our f of x. So what you would do is you would plug in. If we know the equation is supposed to be f of x equals a plus b to the power of, not to the power of, times the natural log of x. That's what that is, natural log. What you do is you plug in your values. Let's choose a point. Which point do y'all want to pick?
3.2.
I hear 3.2. Let's use this as our first point. If I plug that in, what goes in the place of f of x? 4.9. 4.9 would equal a plus b times natural log. And what goes in the place of x? 3.2. I'm going to put that in parentheses there. That would be my first point. Which one do y'all want to choose for a second point? Again, it doesn't matter. 8.8. Let's use this as point 2. Again, it doesn't matter what you choose. You just have to pick a couple here. So I'm going to plug this in. The f of x value is 7. We don't know a and b. The calculator's already found it for us, but we know this is 8.8. Okay, if you were going to solve by hand, you would start like that, and you start working this as a system of equations, like what you learned in algebra. But we don't have to do that in our class. We can use the calculator. So this is AI right here. This would get you the credit. These two equations that I just wrote, these are my two equations. That would get you the credit for AI. Now, for AII, you would just get the values from right here. I'll copy this over. That's our equation right here. And so on this problem, which value is A? Again, round. You can round to 3 decimal places. What's our A value?
6.
Technically, when you round, I should have done this in the last one. You do a squiggly. So it's going to be 2.864. Okay, and then B is approximately means the rounding, 1.818. Good. That right there would be your answer to AII. That would again get you another point. Questions over that part? Okay, let's roll on over into part B now. So it says here the residual plot is provided. Where are the coordinates of the point labeled point R on this residual plot? How could you find out what those coordinates are? What would you do now? Yeah, hit plot on your residuals. Hit that button right there, plot. And once it hits the residuals, I would zoom in or zoom fit the residuals right there. So hit the plot, then zoom fit. R is obviously this point right there. When you click it, there's your value. That's the coordinates of that residual right there. Now this one just says what are the coordinates? So the coordinates are listed right there. That's the answer. The answer on this one, the coordinates would be 1.6 comma negative 0.418. I didn't even ask you. Are those the values you're getting? I didn't even ask you. Did you get the same? Because I could have typed something in wrong. Are y'all getting those values or different values?
Yeah.
Those are the same ones? Okay, great. BII. Does the residual for point R indicate that the model F underestimates or overestimates the value of Y at this X value? What do you think? Is this an overestimate or underestimate? Overestimate, because you're talking about this is the estimate line. This is an overestimate. Overestimate, since the actual data is below the estimate line. So I'm going to fill that in there. I'm going to write back on our notes that this black line, that's the estimate itself. That line is your estimate line or prediction. You could do either word. That line is the estimate. This data represents the actual. The point is this far below the estimate. So the estimate is over it. The actual is under. Our actual is under. Our estimate is over that point. Okay, it says show the data or show the algebra required to determine the coordinates of point R. So here's how you would find those. The residual point is equal to the actual minus the predicted. Y'all remember that? Actual minus predicted. This R value is, the data is 1.6. On our table, did we have 1.6 listed?
Yes.
Yes. The actual data for when we have an x value 1.6 is 3.3. So I'm going to say this is equal to, well, we have the residual right here. We're going to have negative 0.14, no, 418, sorry. The residual of negative 0.418, that was the residual value, is equal to 3.3 minus the predicted. And I haven't found the predicted. What I'm going to do for the predicted, if x is 1.6, I'm just going to type that in. X equals 1.6, so it does the math for me. The predicted amount, no, I'm zoomed on the wrong one now. Let me zoom fit to this equation. The predicted amount was 3.718. 3.718 was the predicted amount. 3.718. If you're wondering where I got that from, I got it from right there. Let me see if I can add all those at once. Yes, I can. Great. All right. Any questions before I move on from here and how I got all that? If you check the math, if you subtract these two numbers, you know what you're going to get? Negative 0.418. That's what that is. If you do the math right there, that's what you would get. Make sense? Okay, you've seen me do a number here. We'll do one more. Sorry, start getting ahead of myself. We're going to do one more, and then I'll send you off. Okay. Okay, let's take a look at example 3 now. It says the table gives the values of the average life expectancy in years for a child born in the United States. Here's our table. Part A, the life expectancy in years of an individual born T years after 2004 can be modeled by the function L given here. Hey, catch this. It said T is the years after 2004. So I'm going to be specific. I'm going to put a T here. They didn't actually give me the T values. A lot of students mess this up. It's years after 2004. So how many years is 2004 after 2004? 0. How many years is 2008 after 2004? 4. 2012? 8. 2016? 12. 2020? And 2023? 19. There's our data that we're going to type in. Those are our T values. And T is in the place of what on this equation? Is T X or Y? T is your X. This would be our Y. Okay, we'll write 3 equations. We'll find A, B, and C and do all that, but I'm going to type in the calculator first. So I'm going to add a table. For the years, I'm going to do 0, 4, 8, 12, 16, and then 19. Now, I forgot to tell you all this. I'm going to go ahead and hit zoom fit on the scatter plot. What type of equation is this? Does it tell you? If you have a squared as your highest power, what is that? Quadratic. So I'm going to choose quadratic here. Quadratic regression. Okay, I did not tell you this. If you want to know how accurate it is, you look at the statistics where it says R squared. Anyone in statistics in here right now? Anybody taking statistics? Have y'all talked about this already? So in statistics, they usually use 2 numbers. They either say if it's better than 0.9, it's good. If it's better than 0.95, it's great. You see how this is 0.9861? That would be a very good model. Anything better, anything higher than 0.9 they consider good. Anything better than 0.95 is really good. Okay, that's a little statistics for you. So this is a good model. That's going to be my equation. Let's fill it in. First, we have to write 3 equations. So the equation they gave us is L of t equals AT squared plus BT plus C. So our first point, you don't actually use the calculator, you just plug in. Are y'all okay if I just use the first 3 points? Okay, I'm going to select these first 3 points. These are the ones I'm going to use. These 3 data points. I'm going to use those 3. So my first one, I'll plug in 0 years with the life expectancy is 76.75 when the year is 0. Now, don't waste your time simplifying this. Just plug in the value and leave it as it is. You don't have to waste your time simplifying it. There's one equation. How many do I have to write? Not two this time. What does it say right there? Three. We're writing three this time. So there's my first point. My second, 77.38 equals a times 4 squared plus b times 4 plus c. Again, don't simplify. And when you substitute with parentheses. And finally, my third equation, 78.19 equals a to the eighth, a times 8 squared plus b times 8 plus c. That right there would be your answer to AI. So your first point comes, those are your three equations. Actually, you don't have to even label that part there. Let me just do it like that. Your first point comes just by plugging in values. That's how you get your first point. Questions over that? No? Okay. Second point comes from getting your equation over here. Again, we need 3 decimals. You need at least 3 decimals. So I'll copy that over. So my A is approximately negative 0.006 or 007? 007 when I round. Your B approximately is, I don't have much room here, 0.247 or 48? 47. And finally, C is approximately 76.662 or 663? 663. That would get your second point. Okay, last little part here for this page. It says, what year does the model predict the life expectancy of a child to return to 77 years? So what is 77 represented by, the X or the Y? The Y. The big key here is I would circle that up and make sure you have your variables correct. This means Y equals 77. That's not the answer, by the way. Some people, when I do that, think that's the answer. I'm not saying the answer is 77. That's what we type in the calculator. Type in Y equals 77. Say that again?
Will I die when I'm 77 years old?
Will I die?
Will I die?
I don't know.
You don't know.
Okay, it says, when will the life expectancy return to 77 years? Okay, look on this. If I zoom out one time, there are 2 possible answers. Which one would be returning to 77? Would it be the first one or the second one? The second. We don't need that first value. That's the one we want right there. That's where we're going to get our answer from. So it says, what year does it predict? Is the year 34 or basically year 35? Would that make sense to say year 35? No. This was years since when? 2004. So the year would be 2004 plus approximately 35 years. I'm going to round on years to the nearest year. So the year will equal 2004 plus 39 years, 35 years. I'm sorry, 35 years. So what year will that be? 2039. For people born in 2039, they're predicting that people born in 2039 would live 77 years again. Now, does that mean that's actually going to be true? No, this would, if you think about it, what this would say if you projected this out, that's people born way out some point in time in here. Let me get there. People born 125 years after 2004 would have a life expectancy of 0. Would that make sense? No, so at some point in time, this model is no longer any good, but that's how it works. Okay. Let's try part B. So now it says, coming back over here, use this given data. BI, it says use the given data to find the average rate of change in life expectancy from t equals 8 to t equals 19. So remember we had the t values earlier? When was t equaling 8? This was 0, 4. Okay, so from 2012 until here's 19. Okay, we want to find the average rate of change. We have a acronym for that. What's the acronym? AROC. How do you find AROC? It's change of y over change of x. Just make sure you plug them in correctly. What are my y values? The top numbers or the bottom numbers? You know what? I'm going to change this. What is y actually represented by and x represented by? Well, x is the years. So it's the change of t over the change of your life expectancy. I'll just do an L for life expectancy. Or you can do L of t if that makes you feel better. So my two time values are, what did they give us? We're using 8 and 19. We're using these two right there. So my two time values, you do this, the second minus the first, so it'd be the 19 minus 8. And in the numerator, it would be 78.87 minus 78.19. I don't want to mess that up. I'm just going to type that whole thing in the calculator. 78.87 minus 78.19 over 19 minus 8. I'm going to write this as a fraction, maybe. No, I won't. I'll just write it as a decimal because it says right here as a decimal approximation. How many decimals do we need in here? We need 3 decimals, so this answer would be 0.0618. The units here, this is years. Life expectancy would be total years divided by years. I'm just going to leave it like that. That's my answer right there. This would be worth a point right there. That's the answer to BI right there. Now, it says on part BII, is everybody tracking with how I got that? Any questions over that part? On BII, it now says, use this average rate of change to estimate the life expectancy of a child born in 2014. Now, here's my problem. Here's what students do wrong all the time. Here's what students do wrong. Y'all ready? It says use what? Here's where many of you might mess up, is you're just going to say, oh, wait, year is 10. I'll just go over here and I'll type in year 10. That's an X, sorry. X of 10 and get this number right there. And that's incorrect. That's not the number we want. It says use the average rate of change. So this is how much it's changing by. We're at year 8 right now. You see this point right here is year 8? Here's how you do this. You write an equation. You use the transformations that we just used last class. And it's this, that the AROC is the same thing as your slope. So you're going to do AROC. And then you're going to plug in your point where your X is a liar and your Y is a truth teller. Now you might be going, wait, where are these values? I'll explain it to you. Our estimate, I'll do Y hat here for estimate because I did that earlier. Our estimate is going to be on this problem, this AROC, 0.0618. That's actually 4 decimals. Times, now they gave us this value right here. This is our X. X is 10. I can put that in there. And now you plug in a point. I'm going to call this one X1, this X1, and I'm going to call this Y1. Is everybody seeing where I'm getting these values? The first point they gave us. So it would be X minus X1 because X is a liar. That's why I'm subtracting the 8. It's a liar. It says positive 8. I'm putting in negative 8. Plus the Y value, which is a truth teller, 78.19. I'm going to type that in the calculator and see what I get. So 0.618 times 10 minus 8. Again, you can simplify if you want. I'm not worried about that because I'm using the calculator. I'll type all that in. I'm getting 78.31. What should we get when we round that? 78.314. That would be your estimate here. 78.314. Now, I want to just contrast this. That's the actual value right there. That's the true value. Did the calculator predict the same answer? Please look. Did the calculator give you the same answer? No. That right there would be, if you went off the calculator, you would be wrong because this did not say use the model. It said use the average rate of change. An average rate of change comes from a line. It's like a slope of a line. Go ahead. Okay, so I just want to be really clear on that. Another way students have asked, can I do it this way? If I know it changes by this much, here's another way. Y'all ready? Starting at year 8, how many years does it take to get to year 10? 2. What you could do is you could start with this amount. So let me delete some of this here. I'm going to delete that and delete this. You could start with this amount here, 78.19. 78.19. If that's what it is in year 8, all you do is add the AROC twice. Why would I add it twice? Because AROC is how much it's changing on average. If this is year 8, you see how that's year 8? Adding it once gets me to year 9. Adding it again, guess what I get now? Thank you. I get the same exact value. See how that also worked? So if that's easier for you, do it that way. Start with year 8 and then just add it however many times, the AROC, add the AROC, however many times you need to get to the year. Does that make sense? Okay. Last part. The average rate of change found in I can be used to estimate the life expectancy for children born in year 2004 plus T, while T is less or greater than 19. It says here, are these estimates found using the average rate of change less than or greater than the life expectancy for the model in AII during the year 2004 plus T when T is greater than 19? Okay, help me out. Is T an X or a Y? X. So go to your calculator. Type in X is greater than 19. Did y'all type that in? The question is our AROC going to overestimate or underestimate compared to this model once X is greater than 19 over here? So let me see if you're understanding. AROC is what type of estimate? Is it linear or is it quadratic? What was the AROC? AROC is linear. Is this slope positive or negative? Positive. So you have some positive slope right here. This model, after, you see how this is concave down? Let's see if you remember your rules. If this estimate is concave down, what does it mean about the AROC when X is greater than 19? Are the AROCs getting are they increasing or are they decreasing if you're concave down? Decreasing. So here, are the estimates found using the average rate of change less than or greater than? You would say the average rate of change, the estimates, I'm starting at this sentence. The estimates found using the average rate of change, rate of change is greater than the life expectancy predicted by model L. The reason is since the model L is what? What did we say about the model L? Go ahead. So the reasons the estimate using the average rate of change found in BI and BII is greater than the life expectancy by model L, I just basically copied those sentences. By model L, I didn't put the when or for, whoops, sorry. or t greater than 19. Here's the sense. Since this model is concave down, the average rate of change would be increasing or decreasing. If the graph is concave down, did the average rates of change increase or decrease?
Decrease.
Decrease. So the reason this estimate right here, the one we're looking at, the one that's not changing, that one on the paper would be greater than the average rate of change after, because they would be decreasing on this interval. They keep decreasing because it's concave down. Make sense? Are you following what I'm saying? Are you all putting this together, or are you forgotten this from earlier this year? If this is concave down, what would it mean about the average rates of change on a concave down? They keep getting smaller and smaller and smaller. This one's locked in from 8 to 19. This one's saying when t is greater than 19. So from 8 to 19, we have some average rate of change, but these, they keep decreasing. If you wanted to know what the average rate of change would look like, I could have typed in this equation right there to show you. Y equals 0.0618. X minus 8 plus 78.31. No, 78.19. Sorry. That's what the average rate of changes look like. But if you keep making more and more average rates of change, they're going to get smaller and smaller and smaller because it's concave down. That kind of clicking with you? This average rate of change is greater because this one was concave down. All right. That was the longest problem ever.
Yeah.
Whew. Example 4. Example 4 now. Hit refresh here. It says a table of ordered pairs is shown. Which function type best models the data in the table? Linear, quadratic, cubic, or rational? Explain your reasoning using characteristics from the table and provide a model equation. All right, let's type these in. How do I get going, or how do I start? Plus table, or you can type in table. Okay, after you get those in, do the zoom fit button. All right, let's start with, what is the equation you know it's not? What do you know it's not? Linear. Okay, come up here, hit the regression, linear. You see how linear is bad? Come down here to the r squared. What number does it show? 0.02. Is that a good model or a bad model? What was the number I said the r squared needs to be good? 0.9 to be good. And if you want it to be considered really good, 0.95 or higher. Make sense? That's bad. Okay, so it's not linear. I'm guessing you know what that is. Quadratic, cubic, or rational. Does that look like a C-curve? Rational. Rational's not even on there. Let's say logarithmic. Does it look like logarithmic? Doesn't work. It's not logarithmic. Okay. Exponential's not on there. Does it look like it's exponential? No. Okay, now I'll do the ones they say. You could try cubic. You could try quadratic. But what does it most look like to you? Quadratic. Look at the r squared. What's that number there? 1. That's the perfect score. So this is quadratic. Now, how would we know it's quadratic? Well, how do we know it's quadratic? The r squared is equal to 1. That's one way you know. If you do a residual like that, I'm going to zoom fit on the residual. Why did it go like that? I was expecting them to literally be on the line. Okay, if it's random, it's good. Does this look random, or does it look like there's a pattern? That looks random. That's a good thing. Go to linear real quick. Choose linear. Do residuals again. Do the residuals on linear, do they look random, or do they look like a pattern? Pattern. That's no good. So this one, we could have known it's quadratic by when you do the residuals. You can see the residuals. By the way, If they're perfectly on the line, then that means it's a perfect model. If they're off the line, then it's not a perfect model, but these are random, so it's good. So there's a few different things you could look at. You could look at the residuals and say there's no pattern, it's a good model. No pattern equals good model. That's why. Let me say, going back to the original, what did the original data points look like to you? The green dots. What did the green dots look like? What shape is that? It looked like a parabola there. Yeah, so there's a bunch of reasons why you could say this is good, but something along those lines is how you get that, okay? I'll add in something, but as long as you put one of those three things that looks like a parabola. So the r squared's one, it looks like a parabola, looks like a parabola. Residuals are random, or no pattern to the residuals. Any of those, these are all different reasons. No pattern to the residuals. Any of those things, let me put this, r squared equals 1, which is greater than 0.9. All these things are different reasons why this is a quadratic. All these things, all those reasons right there would be reasons why you could go with quadratic. Does that make sense? By the way, if you chose cubic, I think cubic might do a 0. Yeah, it chooses basically a 0 for the x cubed. That's why that still works. That's what happened there. All right. I think I'm going to wind down on that. There's some extra things you can look at, but I want you now to go to the back of the packet, and let's try some of these questions here. By the way, pattern or no pattern? No pattern. That's a good residual. Pattern or no pattern? This would be a bad residual if you want to write that in. This is a bad residual. These are talking about residuals. You can look it up here. Bad residual. Okay. Okay. So you're now on your questions. Is that right? All right. There you go. Go for your questions.